So now we have, okay. So as you can see, we have the one radial node and the one angular node. Okay. So I think now we're ready to move on. Okay. Okay. Oh. So I also want to kind of explain a little more what these nodes are. So let's draw, I'm going to draw a graph, kind of. Black. Okay. So let's say we have a graph. So we have R on the x-axis. So R will stand for radius, so distance from the nucleus. And then on the y-axis, we can just have the value of the wave function. So let's look at an s orbital. So 1s orbital. So, so for a 1s orbital, we have kind of something that looks like this, right? So as you can see, there's no region that the electron density is 0. So the 1s orbital has 0 nodes, right? So n-1 is 0, so 0 nodes. Okay, let's use a different color now. Let's look at the 2s orbital. Okay. So we should expect to see 1 node. Oh, but so let's extend that down. So we do. So let me see if I can draw this. So it looks kind of like this. And as you can, so basically, yeah, the wave function can be negative. But when we square it, everything becomes positive, so it's fine. So you can see that we do have 1 node here, right? So this corresponds to our radial node. So when I go to draw the s orbital, the 2s orbital, it looks like this, right? Where this is the the radial node, and then we have 2 regions, which and then one of them I'll shade in, and then the other one I'll leave unshaded, because one of them corresponds to a positive, one of them is positive, and the other one is negative. So these are 2 phases. Okay. And I don't think we need another example since this isn't super important. Oh. Okay. Now we can move on to really the main point of this lecture. So electron configuration. So we have all these orbitals, right? But now we need to fill them, okay? Because like I said, we can only have so many electrons in one orbital, right? Okay. So the electrons fill these orbitals in order of energy, which we call the Aufbau principle. There are some inconsistencies in this order, but we don't need to know about that right now. So this filling orbital, this filling order really determines the overall structure of the periodic table. Okay. And this filling order, handy mnemonic is like Madelung's rule. So this is the idea that you fill orbitals in order of L plus 1. So orbitals with larger values of L plus N, L plus N, fill after orbitals with small values of L plus N. Okay. So, okay. So I want to make another point. Let's imagine we have, let's say, a d orbital. Oh, gigantic fly. Okay. Let's say you have a d orbital. Let's just say it's the 3d orbital. Okay. So can someone tell me what the value of L is?
L should be d orbital, it's 2.
Yeah. Okay, so L equals 2. So given that L equals 2, can someone tell me the possible values of L plus of M sub L?
Excuse me?
What are the possible values of m sub L?
M's of it's 2 or -2.
Yeah, so that's the outermost numbers, but it's all the numbers in the middle too. So it's the set -2,
Oh.
1, 0, 1, 2, right? So, wait a second. Okay. So, I'm trying to manage. Okay. So what does this tell us? How many d orbitals are there then? How many 3d orbitals are there? So we have 5 possible values for m sub L. So that means we can write 5 possible values for the 3d orbital. Does that make sense? Kind of?
Sure.
Right. So, okay. So what I'm trying to say is that you can make 5 different orbitals that have, there are 5 different possible combinations where n equals 3 and L equals 2. Right?
Excuse me, can you repeat that again?
Okay. So we have 5 possible values for m sub L, right?
Yeah.
So that means that there's 5 different orbitals, right? Because each set of each one of these 3 quantum numbers corresponds to an orbital.
So these orbitals don't like appear at the same time, right? They're like 5 possible, like, or so like they wouldn't like be at the same time, right? Like
No, they're all distinct orbitals that can be filled simultaneously.
Okay.
Yeah, because these orbitals are what we call degenerate, since they have the same energy. Yeah, because remember, all m sub L determines is the orientation in space. It doesn't really determine like the shape or the energy of it doesn't determine like the shape and energy of the orbital. Right, so all the orbitals with the same value of m sub L are the same energy. Okay. Okay. Now remember the Pauling exclusion principle that says that, okay, so the spin of the electron is either plus or minus 1/2. So this means that in each orbital, we can put 2 electrons in, right? Because we can either have, a plus 1/2 electron and a minus 1/2 electron. Does that make sense?
So how do we use numbers to identify the electron? Like, how do we use numbers to identify the electrons? Like, why are they like a half or negative a half or something?
Plus, why is the spin plus and minus 1/2?
Yeah.
Fundamental physical reasons, I guess.
Okay.
Physics is not my area of expertise, so I can't answer that question. But yeah, I guess I think there are general classes of particles, right? Like fermions and hadrons and stuff like that, each of which have characteristic spins. So this might be an interesting topic if you want to read more about it on Wikipedia. Okay. So knowing that each orbital can have 2 electrons, right? And that there are 5 different 3D orbitals, how many electrons do you think we can put into the 3D orbitals?
10.
Yeah, so we can put 10 electrons here. Let's just do one more example since this is important. Wow. Oh. I keep on mixing the annotations and the paint stuff. Okay, let's do another one. 2. So can someone tell me the value of the quantum numbers? Hey, Star, can you mute your microphone?
Yeah.
Okay.
So the principal should be 2, right? And then the number of nodes is 1.
Yep.
And L is 1 since it's P. And then so angular node should be 1. And there isn't a radial node since
Okay, that's
total number.
that's good. What about the possible values of M sub L?
It's wait, L is 1, so it's -1, 0, or 1.
Right. So this tells us that how many p orbitals are there?
3.
Right. Okay. Good. And then that means we can have 6 electrons, right?
Yeah.
Okay. So we can put 6 electrons into the 2p orbitals. And this might be a good place to illustrate what I mean by M sub L. So we have 3 orbitals, right? So this means, this is more of a tangent, but it's just a little interesting. So that means we have 1 p orbital along the z-axis. 1 p orbital along the y-axis, and 1 along the x-axis. And these are the py, pz, and the px orbitals. But that's just what I want to illustrate by what M sub L really means. You don't need to actually memorize that. Yeah. Okay. This is that kind of stuff kind of becomes important if you want to talk about like MO theory or crystal field theory, but those are not in the AP curriculum, so we're not going to talk about that. Okay, so now we can start filling electrons. So I got this nice picture. Let me see if I can zoom out a bit. Oh, the picture's gone. Let me just find one. Let me just get the list so that I don't. Yeah, you should memorize this list, but for now we can just use a picture. Okay, here we go. Okay, so this picture tells us the order that the electrons will fill, the order that will fill the orbitals, right? Okay, so this tells us that the first orbital to fill is the 1s, right? And then we go by diagonals. So then the 2s, then the 2p, the 3s, the 3p, the 4s, 3d, 4p, 5s, and then you get the idea, right? Okay. So let's look at the, okay. So let's look at the first few elements. So we'll just go in order. So let's consider hydrogen. So looking at the periodic table, can you tell me how many electrons are in an atom of hydrogen?
There's only the number of protons. Are they the same?
Okay. So remember, so we're talking about neutral atoms, right?
Oh.
So the number of protons and neutrons is the same. Yeah, I forgot to mention that.
So it's 1.
Yep. So we have 1 electron, and what's the first? So let's start with the low. We have to start with the lowest energy orbital. So the first electron to fill is what, right? It's the. So what orbital do we fill first?
The first one. So there's only 1 orbital.
Yeah. Let's just go in order. So we fill the 1s orbital first, right?
Yeah.
Looking at the diagram. And then we put 1 electron in there.
and that's it. We don't have any more.
That's it. Good. Yep. Now let's look at helium with its 2 electrons. So remember, we can put 2 electrons in the 1s orbital, right?
Yeah.
So it's just 1s2, and that's it. Okay, now let's look at lithium. So this one has 3 electrons, right?
Yeah.
So we can do 1s2, but now the 1s orbitals are filled, right?
So it's 2s orbitals, and there's only 1 electron in that orbital.
Yep. So now we do the 2s and we put, oh, my bad.
Well, 1.
Yeah, 1. Okay. So we have to move on to the 2s orbitals.
Wait, excuse me. Well, why can there be like 2 electrons in a 1s orbital?
Well, remember that, yeah, you're right that there's only one 1s orbital. But each orbital can fit 2 electrons because the electron spin is either plus or minus 1/2. So we can put a plus 1/2 electron and a minus 1/2 electron in the same orbital.
So there is one possible m sub.
Yeah, right? There's only one possible value of m sub l.
Yeah.
Right?
And
But you
there are
have 2 possible values of m sub l.
Right. Right.
Okay. So then what do you think, can someone tell me the electron configuration of beryllium?
It's 1s and 2 electrons and 2s 2 electrons.
Yep. Okay.
The first one is also 2.
Oh,
Okay.
sorry. Yeah. Okay. So what I want you to notice is that we've been so far we've been hanging out in this region of the periodic table, right?
Yeah.
And in that region, we're filling the s orbitals, right?
Yes.
So we call that area of the periodic table the s block. And what I hope to show you guys is that the structure of the periodic table is related to electron configuration. Okay. So now let's do boron, the most boring element, right? Okay. So we have 5 electrons, and we already know to fill the 1s2 and the 2s2. Okay, so now what do we do next?
2p.
Okay, and then we put 1 electron in there, right?
Right.
So now let's just skip to neon. Okay. So can someone tell me what the electron configuration should be here?
1s2, 2s2, and 2p2. No, wait. It's neon. So it's 2p.
Okay, well, let's see. Let's see how the periodic table can help us here. So we started from boron. So boron is 1 p electron, right? With boron, we put 1 electron into the p orbitals instead of 2 p orbitals, right?
Yeah.
So now for carbon, we add another electron, then another electron, then another electron, then another electron, and another electron. So that's 6 electrons, right?
Yeah, and there can be 6 electrons in 2p because.
Right. So now the 2p orbitals are filled. So in this region of the I have to switch to yellow. Okay. So in this region of the periodic table, we're filling the p orbitals. So we call that the p block. Does that make sense?
Excluding helium, right?
Yeah. Helium can. Yeah. I wouldn't worry about hydrogen and helium too much. Their position on the periodic table is kind of funny. So just, yeah. We do this because helium has the properties of the other elements below it. So we put it like there. And then, yeah. But we're not going to worry about too much about those minor details. Okay. So let's do silicon. Okay. So what do you think the electron configuration of silicon is?
Wait a minute. So
Okay.
it's 1s2, and then 2s2, and that's for sure. And then 2p6, and then there are 6 left. It's 3s2,
Okay.
and then 3p 4.
Wait, so
No, 6. No, 4. Yeah, 4.
wait, okay. So you're almost right. So you're right, we have to start filling the 3p. But okay. So this okay. Let me switch to a okay. Okay, so we're done filling the 3s orbital here, right?
Yeah.
So now we're over here, and this is where we need to start filling the 3p orbitals. So now we have only 2 electrons in the 3p orbital, right?
Right.
So 2. And also, if you want to double check your work, notice that all of these numbers need to sum together to the atomic number.
So sorry, I didn't see the I. I got it confused with the S.
Oh, sulfur? Okay.
Yeah.
Got it. Okay. That's fine. Okay, let's just do a tricky example. I'll just walk you through this one because it's a bit more. Okay. Yeah. Okay, so now let's just do nickel, right? Okay. So now okay. So 1s2, 2s2, 2p6, 3s2. Okay. And now we need to fill the 3p orbitals, right?
Where is this nickel?
Oh, nickel?
Yeah.
Let me circle it.
Oh. Okay.
Yeah. As you study more chemistry, you'll start to like memorize this stuff. So don't worry if you don't know the way around the periodic table yet. Okay?
And then 4s2.
Yeah. So now we need to do 4s2 because the 3p orbitals are filled.
And then
How many d electrons are there? So we start from scandium and we count up from scandium. So 1, 2.
8.
Oh, by the way, can you see the pen icon?
Yeah, I can.
You can see the pen, right?
Right.
Okay.
I can see everything on your screen.
Okay. 1, 2, 3, 4, 5, 6, 7, 8. Right?
And that's the number of no. Yeah, that's number of 3D.
Yep. So what do you think this block of the periodic table is called?
It's called D block.
Yeah. Okay. Yeah. And this is the F block. Okay. So now let's talk. Is it okay if I clear all this stuff?
Sure. Yeah.
Okay. Now let's talk about how to abbreviate these electron configurations. Because as you can imagine, these electron configurations start to get very long. Okay. So basically, what we do to abbreviate this is we start from, okay, this column, the noble gases, and then we take their electron configurations and we just add onto it. So to illustrate this, let's just start with neon. Okay, neon. 1s2, 2s2, 2p6, right?
Yeah.
Now let's do phosphorus. So 1s2, 2s2, 2p6, 3s2, and then 3p3, right?
Right.
Does everyone see why that is?
I see.
So notice this part are the same. So if you can cross that out, And then we can replace it with this. So we put argon and, oh, not argon, neon. Neon in brackets. And then we just write 3s2, 3p3.
Oh, so yeah.
So now let's do the abbreviated noble gas. Let's do the abbreviated electron configuration for cesium, which I'll circle on the periodic table. Cesium. So the full electron configuration for cesium would be very long, right? But what's the abbreviated one? Can someone tell me what that would be?
Which line is it on the
Oh,
periodic?
it's the one in the yellow
Oh.
circle.
Yeah, I can see. So it's a bracket Rn.
Oh, wait. So you need to add on, right?
Yeah.
So Rn is 86 while Cs is 55. So radon actually has more electrons than cesium.
So it's bracket K. Is that K? Ke?
Oh, that's Xe. Xe.
Oh, Xe. And then it should be 4D1.
Okay, wait. So remember, cesium is in the S block.
Oh,
Right.
5S or 6S.
Yeah, 6s. 6s1. Let me
Because
just
it's
try to
on
illustrate.
the sixth line.
Yeah, I picked a bad example. So this is the 1s, then 2s, 3s, 4s, 5s, 6s, and 7s, right?
Right.
Then here we fill the 2p, 3p, 4p, 5p, 6p, and 7p, right?
Ah.
Here we fill the 3d, 4d, 5d, and 6d, right?
And 4F, 5F.
And then the 4f and the 5f, right? That's right. Just to point that out. So that might help with the heavier elements.
Yeah.
Okay, clear everything. And I think we still need to talk about Hund's rule. So, okay. Yeah, we still need to talk about Hund's rule. So, this has to do with the spin of the electron. So,
S spin.
spin. S-P-I-N. Okay.
Is it like M sub S spin? Is this?
Yeah, M sub S. So an electron with a plus 1/2 spin is usually represented as an upwards facing fishhook arrow. And then for a negative 1/2, it's downwards facing, right? Okay, let's do an example. Okay, the 5d electrons. So how many 5d orbitals are there?
10.
Okay, so we can fit 10 electrons, right?
Oh, right.
But there's only 5 orbitals,
Oh,
right?
and there are 2 spins. Yeah.
Okay. Yeah, but there's 10 electrons, right? Okay. Okay. So I'll represent these orbitals as these lines. Okay? Does that make sense?
Yeah.
We can give them labels if we want. So x, y, y, z, x, z, squared minus y squared, and z squared. You don't need to know the labels, but they're kind of cool, I guess. Okay. So now let's start filling these. It doesn't matter which orbital we start with since they're all the same energy, but we'll just go from left to right. Okay. So we put in 1 electron. Now we have a choice. We can either put another electron into the XY orbital, or we could put it into a different orbital. Well, it turns out it's more energetically favorable to put it into a different orbital. Yeah. Because you know that electrons repel each other, right? So we don't want to put them into the same orbital unless we have to. And there's the hotel room analogy. So like imagine you and your friends are getting hotel rooms, right? And if you have 5 hotel rooms, you're not all going to go into the same room. You're gonna split it up if you can, and then if you have to, if there's not enough space, you'll start putting the same people into the same room. Okay.